So I started recording.
Right before we start the seminar, there's just something Mr. Bullock and I want to review. It's very important, especially when it comes to absences in terms of your teachers. Our teachers too, we have kids, and there are going to be some days that we're not able to make it to school, and maybe you have a test scheduled for that day. As much as possible, from the time you get your test authorization signed, you have 6 days to write your test. If you are waiting to the day of the test to get your test authorization signed, you are going to run into complications if your teacher is not there that day. So, we're not in the quad system anymore. It is imperative that no one else signs your test slip besides your teacher. Mr. Bullock signs his students. I sign my students. If Mr. Bullock or myself are absent on that day, you can wait for an additional day. You can wait to write it the next day when we are back. And only for rare circumstances, Mr. Bullock?
Yeah.
If, for example, you have to stay home with your daughter for multiple days, then you can come to only me. So Mr. Bullock students would come to the other calculus teacher, which is me. I would send Mr. Bullock an email, and once he confirms that you can write the test, then I will sign your test slip. And same with myself. If I'm away for a week and you can go see Mr. Bullock, he will email me for confirmation. So it's very important that you do not go to a supply teacher, you don't go to any other teacher in the department, just the 2 of us for your calculus course. We've been really nice about cutting a lot of the tests out of the course, and we do not want that to be taken advantage of. So please, please, please follow those rules. We'll make an announcement on our D2L as well. But you can wait one more day if one of us is absent. Okay?
Basically, if you're planning well, though, right? Remember, you do have a window of time to be able to write a test, right? So if you are planning on writing a test, 5-6 days from now, then you should come to see your teacher to get your test slip signed and then wait that time. If we don't happen to be here, that's just one less day from the day that you were planning on writing it anyways, right? So we really shouldn't have too many issues with this at all. We just wanted to communicate that the only ones that should be signing those test slips should be your subject teacher, or barring some significant extenuating circumstance, then you can come see the other teacher. Ms. Albert and I are the only teachers teaching calculus. Okay.
And kids, please, this is just a Zoom for Mr. Bullock and myself. Don't join the Zoom link. I don't know how.
Oh, there might be one student who is at home who messaged me, so Sean can, he can come.
Typically, we do not do this. This Zoom is just for our recording purposes. Go back to our
McDonald, he reports to the main office. Heather McDonald to the office.
Okay, anything else?
questions. We're all clear on that. Okay, so we're going to start our introduction to vectors, which is unit 3 and 4. As you work through the unit guides attached to vectors, you're going to discover that there's a lot of content, but there used to be a very difficult test that we have cut out. So for your university deadlines, let's be clear, you have to have your unit 2 test written and in the computer, and you will have to have the vectors unit or one of the vectors units done, meaning you have to show your teacher your completed unit work, get your signature in your agenda, and you'll going to give you an option for an assignment. Actually, to take a test if you want to take a test. If you really want to take a test, that will be an option. Or you can do a video of a complicated vectors problem where you're going to pretend that you're the teacher and you're going to walk me through how you would teach 1 or 2 vectors questions. We're still figuring that out. Or if you're taking grade 12 physics right now, you can request that with your physics course. And Ms. Malloy will be giving a presentation with us with all of the grade 12s because vectors is a concept that is really a marriage between calculus and physics. So if you are a physics student or a friend of a physics student, you will go to the physics grade 12 lab. You will observe the lab, obviously if you are a physics student participating in the lab, and then you're going to do a reflection for your calculus course about the lab. Okay, so I've given 3 to 4 options. 4 options if you really want to write a vectors test. I have a good one for you. But if you don't, there are 3 other options for what you can do instead, and that's for unit 4. So we'll have that all ready for you. We're just ironing out the kinks in that. The first vectors unit, which is unit 3, has already been posted on our D2L.
So on the D2Ls, you can find under the unit guides, right? It's actually starting from the first one is vectors, unit 1, and then it just goes from there, okay? We'll reorder them to kind of correspond with the actual unit numbers that you guys have been learning about. So as you know, we kind of have to reorganize some things. But just on the topic of university applications as well, each of you should have received your OUAC pins. Just put up your hand if you've received that from your TA. Okay, that's really great. Those are really important documents. Just make sure that if you have yet to receive one, you're in communication with your teacher advisor about that because it should have gone to them first, okay? Yeah, just to make sure that all your ducks are in a row for that. Okay. Anything else, Miss Albert, before we get rolling here?
No, I think that's it. Today's seminar is really meant as an introduction. For those who took grade 11 physics, a lot of this is going to already be familiar to you, but there is a slight difference in the way we do application problems in the world of physics compared to the world of calculus. And you will really, that will be reinforced maybe in your first year calc course. But again, we're only testing you on the absolute essential concepts in calculus, and vectors is just one of those things that is and has amazing real world applications. But if you don't take a test, it's not going to be a issue next year. Okay, so we have some terminology for vectors. When we talk about vectors, they always have a direction and they have a magnitude. That's kind of the theme of your entire unit. We're going to be exploring those concepts of direction and magnitude. Now, a scalar quantity describes magnitude or size only. Those are things that have no direction. So in science, your mass, speed, distance, temperature, those are all examples of scalar quantities, while a vector is a mathematical quantity that has both a magnitude and direction. So velocity and force, important concepts in physics, in the world of physics, those all are examples of vectors, and they're represented with directed line segments, which you are going to be working with through the first 2 vectors units that have to deal with geometric vectors. Just put that in as an example for application problems. So police at an accident scene need to consider the momentum of cars of different masses traveling in different directions. Pilots, there's lots of problems on the original vector test that have to do with aviation because you're often looking with speed and direction. So there's lots of real world applications of vectors.
Okay. So I speak this a bit bigger.
So just some notation, and some properties of vectors that we can talk about to kind of start here. So we denote this as a vector AB. So a vector you can write as designating endpoints of a line segment. So if one of the endpoints is A, the other is B, we kind of put an arrow above each of them to signify that it's a vector. So we could say that vector AB has a starting point A, ends at B. But you more typically, though, you kind of write it as a singular variable value. So instead of constantly writing vector AB as its endpoints, we might just give the entire vector a label, and we'll just call that vector B, for example. Okay, so both are used. When we're talking about the magnitude or size of a vector, we use the absolute value notation. So those are those two vertical lines that surround that vector. Okay, and the reason we use that is because we're talking about magnitude. So magnitude or length is always a positive value. Okay, so when we're talking about a vector length or its magnitude, we have to make sure we're using the appropriate notation for that. So it's always a non-negative value. Okay, always a positive distance.
And if you just before we go to the
Yeah.
next slide, just really quickly go over to the diagram here. So this is really important. It might seem intuitive, but when we get to the vector rules, you might want to include this in your notes. So we always have the starting point of your vector is called the tail of the vector. And where you see the little arrowhead pointing to the direction, that is the head of the vector or the tip of the vector. And the reason why that's important, when we get into the rules, we'll have the tail-to-tail rule or the tip-to-tail rule, and you'll have to distinguish that the tail is actually the starting point. Sometimes students easily confuse that. Tail is your starting point, the tip is your ending point of the vector.
Okay. Okay, so directionally, how can we express these things? So we're going to be talking about rotation, and there are a few different ways that you can use language to signify this direction that we can give. Okay, so we're going to talk about each of them. So the first way we can do this is as an angle moving counterclockwise with respect to a horizontal line. You guys might, if you remember back from grade 11, if you did.
Please just look around the students' seat of Ms. Grace's backpack. He says it's a gray backpack and it's a Novo laptop with a charger. If you can see that it's in your area, he thought maybe English, but if you could just have a look around and if you find it, please bring it down to the office. He's anxious to get it back.
Yeah. Okay, so back when we did trigonometry in grade 11 and we learned about terminal arms and angles of rotation, you always started at this horizontal. Okay, so always just horizontal to the ground, parallel to the ground, and you rotate counterclockwise. Okay, that angle of rotation with respect to the horizontal line is one way that we can show the directional for a vector. So for example, for this diagram here, we would say that the magnitude is 14 centimeters at 110 degrees to the horizontal. Okay, so you start horizontal, rotate counterclockwise, and that angle is signified there. So another example, starting from the horizontal again, but this time we're only rotating 30 degrees to the horizontal. Our magnitude here is 5 kilometers, and we just say it's at 30 degrees to the horizontal. Okay, sorry, Liam.
How would you represent the first
Yeah, we're gonna go through that. We're gonna go through that. Okay, good question. Yeah.
That's a great question, because we're gonna look at true bearing and quadrant bearing to answer Liam's question. So the last example, whenever you see in your unit work on a test, the words to the horizontal, that means you're moving in a counter, you're analyzing in a counterclockwise direction. But for true bearing, which I believe is the next slide, that's when we are starting from the north and we're measuring the angle in a clockwise direction. That's called a true bearing. Over here, if I'm starting from the north and I'm moving in a clockwise direction, I'm focused at this angle, 135 degrees. So my vector U has a magnitude of 2.3 kilometers at a true bearing of 135 degrees. If I miss or if I mix that up strategies, I would accidentally be looking for a counterclockwise angle, and that would not satisfy the definition of a true bearing. You can see that in the movies, a hundred day of true bearing. Now with true bearing, I believe we always have, you'll see this 0, 6, 0, 0, 60 degrees. You always have to have 3 digits for a true bearing, and that's why there is a 0 in front of the 60 degrees. So the angle on the bottom, we have a magnitude of 2 kilometers at a true bearing of 60 degrees. Again, starting from the north, going to the actual vector. And you'll notice that if you had to draw these vectors, they have to be to scale. So in the first example, every centimeter represents a kilometer. Same thing with the other example. In physics, you have to come up with a scale when you're drawing your vectors. And but I don't think we're going to do that in our topic discussion.
Okay, so sketches are open. Okay, the third one is called quadrant bearing. And so if you remember, the first one we did horizontal is rotations counterclockwise. The true bearing is rotations clockwise. This type of directional quantity we can give this depends on the quadrant. It's always going to be between 0 and 90 degrees. And the language we use is either east or west of, north or south. Okay, so it's dependent upon which quadrant your direction is in and whether you're referencing it to the north or to the south. So for example, this first diagram here, you see that the units we're using is N. Does anyone know what that N stands for? Just curious. What unit? In physics, maybe? Yeah, it's a Newton. So 9.8 newtons. Okay, you might see that if you take physics course. So that's our magnitude of vector U there. But you can see that we are in quadrant number 3. If you guys remember the quadrants, right? Upper right is 1, and then we rotate counterclockwise 2, 3, 4. Since we're in quadrant 3, what we would say is we're rotating from the south, okay, at a bearing of, and the language we use is 35 degrees west of south. That's how you would say that. Okay, so 35 degrees west of south. We're starting in quadrant 3. That's where our vector is located. But we have to rotate 35 degrees from this pole here in order to get that directional point. Okay. For the second one, we're in quadrant 2. Okay. So now we're going to be not referencing the south, because the south would be quadrants 3 and 4, but we're referencing this north. Okay. And to get to where our vector has been rotated from the north here, we've rotated 80 degrees from that y-axis north pole, I guess we call it. Okay. The magnitude of this vector is 25 kilometers per hour. And the language, how we would say this is it's been the quadrant bearing of 80 degrees west of north. Okay. So that's the language we use. That's how we know to. Okay.
Both said west of north, and that's this is where students get confused, because when you're writing it, it's north 80 degrees west. But when you're trying to understand it in your head to get figure out how to draw it, we are talking about west of north, right? So just make a note of that. And when it comes to the application problems, this I would say would be the number 1 concept that confuses students. We're talking about quadrant bearing.
And just speaking of the language, because sometimes it gets a little bit confusing or counterintuitive for directionally what's happening. One other common one that I run into with students is if you have a question that says a wind from the west, right, or a wind from the east, okay, it's actually directionally opposite of probably what you would think. A wind from the west means it's traveling east and vice versa. Does that make sense to you guys? Okay, so just make sure, like if you come across a question like that, that you get your direction correctly. And it explains in the textbook, but it's just a common error.
So when you're representing a quadrant
yeah,
is north or south always going to be the first direction?
Right here for this first,
yeah,
yes. The second one will always be east. Okay. Which one it is dependent upon what quadrant you're vectorizing. Okay. Yep.
so that's like that's how it's going to be.
exactly represented as
Yes,
east.
we would never write west, then 80 degrees, then north. It's always
Mm.
north or south, then east.
Okay, good questions.
Okay, so if you're gonna convert the following and we wanna focus, say we're just given the words, this would be a test question, but because we're not giving you a test, we put everything at once. Write the true bearing 150 degrees as a quadrant bearing, okay? When we're drawing this out, true bearing starts from the north, and then we move 150 degrees to my vector, right? But if we're converting that to a quadrant bearing, the vector is in, can someone tell me what quadrant the vector is in? 4, right? So we have, we're in quadrant 4, we're not starting from the north, we're starting from the south, and I'm moving towards the east. So I'm interested in this angle over here, which I know from the north and south line, that makes 180 degrees. So if I take 180 degrees and subtract the 150, I get this smaller angle of 30 degrees. Okay, so we have our, we're starting from the south and moving towards the east, south 30 degrees.
Let me just zoom in here, but so this is the second example, right? The quadrant bearing 50 degrees west of north as a true bearing. Okay, so this is kind of the little bit of the opposite. We're starting with this vector ending up in, or beginning, sorry, in quadrant number 2. Since we have a west of north, we know we're going to be in quadrant 2, moving west of the North Pole here. Rotation of 50 degrees from that point leads us to this vector, okay? But it's asking us to state this as a true bearing. So true bearing is being rotated the opposite direction from north. And for this, we need to remember that a full rotation is 360 degrees. So if I add those two angles, so 50 plus some angle should be 360, or conversely, you can think of it as 360 subtract 50 to get our true bearing angle of 310 degrees, okay? Both of those are equivalent ways of writing the same thing. What you guys need to be proficient at is converting between them and knowing when you see it, when we have a problem that involves that particular language, how to draw it mostly, okay? All right.
And specifically, if you're a physics student, you will know that since this is often a test that students struggle with in physics and calculus, there are so many resources on YouTube about aviation problems, vectors problems. There's so many resources out there. It is a challenging concept when you're studying for a test because there's a plethora of options that we could give you. But when you're working towards your unit guide, I encourage you to work with your friends and figure it out together, kind of work together. You're not going to be tested on it. It won't be on any final exam. Just appreciate the concept of learning these things together and working it out, like working out a logic problem. And we've taken the anxiety off for having to write a test for this unit. That doesn't happen at all. The next portion, we're going to go to, this
Well, there's
one,
just further
I
examples,
have
but
some more examples
yeah.
just for practice.
but I think we can go for it.
Yeah. Now we have to move into the concept of defining things because before we can move into real application problems, they're not always going to be so simple as our true bearing and quadrant bearing conversions. We have to know some rules about vectors. So parallel vectors have the same or opposite direction, but not necessarily the same magnitude. So I can say that vector AB and vector BC are parallel, and vectors AB and CD are parallel, so moving in the same direction or moving in the opposite direction. But because they don't have the same magnitude, just because they have the same direction. That's parallel vectors.
So just recognize too that these arrows that you see in the diagram have nothing to do with the vectors themselves. You might remember that notation from grade 9, right? Those are just showing that they are parallel. That's what those two arrows mean, okay? To find the direction, you can either look at the notation to determine which is the end and the tail point, okay? But the point is, they don't need to be going in the same direction or the same size, okay? In order to be parallel.
This is
Okay.
going to be contrasted if we ask you to define equivalent vectors. Equivalent vectors do have to point in the same direction and have the same magnitude. Oh, that's the next one. Sorry,
Yep.
I didn't know that.
That's okay. So you can continue, Ms. Allen.
Yeah, so vectors that have the same magnitude and direction are equivalent vectors. It says the location of the vector does not matter. So it can be anywhere on your shape, object, in your question, as long as they are pointing in the same direction and have the same magnitude. I think we have some complex, what do we call platonic solids in different shapes that are in, I'm not sure if it was this new textbook or an older textbook, but you have to be able to identify parallel vectors, equivalent vectors, and opposite vectors.
Okay, so opposite vectors. So these vectors have the same magnitude, but they point in opposite directions, okay? So if we look at, let's say, vector AB here and vector, the second one. So the first thing I want to notice is the magnitude of each is the same. So we could denote that using our absolute value symbols, okay? But they point in opposite directions. Therefore, vector AB does not equal vector BA. Okay, the directions must be the same in order to be equal to each other, but their magnitude is equal. Okay, you can write an expression for an opposite vector by placing a negative sign in front of it or by reversing the order of the letters. Okay, so if we have vector AB, you could either write the opposite of it as negative vector AB, or you could swap the A and the B, so it becomes positive BA, vector BA. Okay. So there's two ways to denote that.
But identifying, remember our definition of the vector that we start at the tail and we move towards the tip, the point of the arrow, right? Start at the tail, move towards the arrow, the tip. We never start at the arrow.
Okay, so an example, given vector AB, draw an equivalent vector CD and opposite vector EF. Write the equations to show the relationship between the vectors. So if we're given vector AB to start, an equivalent vector would just have the same magnitude and direction. It can have a different location, like it doesn't have to be right on top of each other, right? But as long as the magnitude and direction are the same, then it's an equivalent vector. For an opposite vector, it's going to have the same magnitude, okay, but just the opposite direction if you're drawing it as a sketch. And you'll be doing lots of sketches with vectors, okay? Notationally, we can just say that vector AB is equal to vector CD, and that vector AB is equal to the negative or minus vector BA, okay? So a couple different ways you can notate. Well, that's a good question. Yeah, it is. My microphone's working, yeah. Oh, but your laptop is muted. Oh, so I don't know. That's a good question, actually, because it might be picking up from yours if you're recording, right? So your microphone, I don't know. Maybe just unmute your microphone. Mostly.
See that? We might not have sound for the first little bit, but that's okay. Okay, let's continue. Option.
Okay. So when you add two or more vectors together, what you are doing is finding a singular vector. Okay, so you add two or more, you always end up with a singular vector, and we call that the resultant. So it's a very specific name, okay? That vector has the same effect as the original vectors applied one after the other. So if you have a bunch of different vectors, you do some operations with them, what you end up with is called the resultant. It's sort of the overall behavior once you've done all the operations with those other vectors, okay? So there's two ways to determine the sum of vectors. So we're going to be talking about operations with vectors. So let me just make this first one a bit bigger so we can see that a little bit more. Okay. So if we're determining the sum of any two vectors A and B, we'll just call them, if they're arranged tail to tail, so this is one way you can do it, connect the tails of the vectors together, okay? And you're going to complete the parallelogram formed by the two vectors. So basically, the top of that parallelogram will have the same magnitude and direction, and will be parallel as the base of the parallelogram, and same with the other side, right? We'll have the same magnitude and direction as the vector that's adjacent to it. So you create a parallelogram, and then you're going to draw a new vector from the corner of where those tails met over to the opposite edge of your parallelogram. Okay, does that make sense? So tail to tail, construct a parallelogram, create a new vector that goes from the tail to tail point to the opposite end of the parallelogram. That vector which you created is the new vector which represents the sum of the original two vectors. Okay.
And that method is not as popular and harder to work with sometimes than the other strategy for adding vectors, which is the tip to tail method. I always wondered why they call it tip to tail, because we take the second vector and the tail of the second vector has to be at the tip of the first vector. That's how we're going to lay them out, right? The tail of the second vector at the tip of the first vector. And the resultant is always from the tail of the first vector to the tip of the second vector. That's how we draw out our resultant to translate this math into something practical. And you don't want to mix that up, right? If I accidentally start at my second vector and move to my first, then I'm not solving the question properly. So you really want to practice. The tip to tail method is probably the most popular method for adding vectors.
Okay, hopefully you guys can see that geometrically it's equivalent. Right? That vector you draw, whether you construct a parallelogram or you choose to do the tip to tail, your magnitude, direction of your newly constructed vector will be equal, no matter which way you do it. Okay, so as Ms. Albert said, typically tip to tail, a little bit easier, but both will work. Okay. Okay, what if we add opposite vectors? So when two opposite vectors are added, you still have a resultant, but that's a special name. We call it the zero vector. Okay, this means that the combination of a vector and its opposite will always result in this zero vector. Okay, so think about if you just look at the diagram that we have here. We've got two vectors that are the opposites of each other, right? They have the same magnitude, direction, but same magnitude but opposite directions, rather. Okay, so adding these two vectors together. And look how we notate this, is equal to our zero vector. So it's just a zero with a little arrow above it. Okay, so whenever we add opposite vectors together, we'll always end up with this as our result.
And actually, another way of writing this that often helped me when I was studying this concept, if I have my vector AB and I want to write this as negative because it's in the opposite direction, I want to write the second vector as negative AB. Well, we can now easily see that the positive vector and the negative vector cancel each other out to come up with the zero vector. So that when you're dealing with, is it the algebraic vectors or the preliminary part of your homework, sometimes it helps to write it like that.
Okay, so let's say we've done the sum of vectors, we found our zero vector. To do difference of vectors, so let's say we're subtracting them. We have two options again, just like we had when we were doing summation. Okay, so one thing you can try is what's called adding the opposite. So the difference between those two vectors can be found by adding the opposite of vector B to vector A using the triangle law of addition. Okay, so for example, this kind of ties in with what Ms. Albert was talking about. So we're adding these two, subtracting vector B from vector A. So you can see it in our diagram here. This property, though, of adding the negative vector B is the same as finding the difference between those two vectors. So what you can do is you can construct them again. See how we put from tip to tail, okay? And then construct your vector in triangle. So let's do vector by connecting the tip of the original to the tail of the one that you're subtracting, okay? And we can write that simply as vector A minus vector B. So that's one way.
The other strategy will be the tail to tail method, where we place, obviously, the two vectors from have their tails touch each other. And the second vector, we are going to, the resultant is always, and it's important to get the direction of the resultant right. So in order to get the correct direction, the tail of the resultant has to start at the tip of the second vector, and it has to meet the tip of the first vector. If you confuse those two, then your direction of your resultant will not be correct. So both methods, as Mr. Bullock mentioned, will give you the same result at the end. It depends on what strategy you're comfortable with. And that's why it helps when you're comparing your results with a friend, because you could have used different strategies, but came up with the same resultant and a similar solution.
Okay, so let's look at an example here. So let's say we are given vector A, B, and C as shown below. So here they are. Like this. And we want to construct a diagram that shows us vector A subtract vector B plus vector C. Okay. So what you could do, and I think I can kind of move these around a bit. So what we'll do is we'll start by finding the difference. So vector A minus vector B. And you can use either of the strategies from the previous slide, but what we'll do is we'll connect them tip to tip like this, as was stated. So we're doing this method here, okay? That's the first step. And then what you can do is draw the resultant vector of that operation. So I can draw that in. Let me just get rid of this. Let's use this, and maybe we could do this. Okay, so that red dashed line is our resultant vector of the difference of those two, just from the last rule we used. And now we could add vector C from that new vector. So what we're going to do for this one, if we're adding, is simply go tip to tail. And I'll put, I might just have to move all this stuff. Well, I'm just going to zoom out to do this. Switch, there we go. So let's, oh, that's locked, that's why. Can I do this? There we go. So let's move this vector here. Okay, I'll zoom back in. There we go. And now, if I add this vector C here, I can draw from this point. We'll use that green line. That's our result. Okay. So when you're doing your diagrams, you could go step by step like this, or you could do the operations and then just draw your resultant vector. That's fine. Okay. But yep, go ahead.
And this is why, like, the cool thing about vectors is you can do this in opposite ways. So I'm working with Mr. Bullock on an assignment, and he shows me that solution, and that is one way of solving it. But what if I want to do my solution like this? So I have vector A. I want to add, so use my tip to tail strategy to add the opposite vector, and then add in vector C. So that would also give me a similar, the right solution as well. So I would take my vector, this is vector A, instead of using vector B like this, I would add in the same vector, same magnitude, but opposite directions. I just want to kind of make that accurate here. I don't know where the eraser is.
Oh, you
It's
can just use
disappeared.
the one.
Let's pretend that it is the same magnitude. And then I can draw my vector C like this and draw my resultant. So I have my resultant from the tail of, let's see, well, that's another option of drawing your resultant. I don't have my tools with me.
I can
Yeah,
Let me try.
yeah.
So I
Let's
think we'll
move
do-
that over.
so do like
But,
this.
So using the opposite, I just wanted to show you using the opposite vector could also give me a solution that, there we go. That's the way the resultant should look like. And that will be very similar to the resultant in the first example using different strategies, okay? Using different strategies.
Basically, it doesn't matter which method you use. We didn't change the green dash line to the red dash line. We just changed the orientation of the vectors based on operationally how we're going to write the original problem. And no matter which way we do it, our resultants are the same. Okay, so you could do it different from someone else. Operationally, your diagram could be completely different, but if you've done it correctly, your resultants will be equivalent. Okay.
Let's do an example for all of you to try to wake you up a little bit. So we're going to put something on the board and we want you to talk to the person next to you to try to find equivalent vectors as well as some adding and subtracting of vectors based on, I think it's the box problem.
Oh, sure. Yeah.
Perfect. So see if we can fit that all on one screen.
Okay.
So we have vector OA represented by vector A. The coordinates, I should say, OC are represented by vector B, and OD are represented by vector C. We want you to try to come up with some statements of equivalent vectors, and in some cases, we're asking you to find the resultant of different vectors. Okay, so do you want to go ahead and try that? You have something very similar in your unit work as well.
There's more than one right way to do this, right? So
Yeah.
see if you can come up with a couple different ways too.
Maybe this is a portion where we can reveal the answers, but if you're confused about something, you can come see your calculus teacher for clarification.
Because I'm not.
No, it's on my laptop. I mean, it has to be on. Yeah. The one that has all the yeah. Well, but the speaker was on. So usually I have my speaker on. So it should I'm sorry, I have my microphone. Can we have some potential answers for the first one? I have an equivalent vector to vector BC. Shout it out. Okay, does everyone agree with that? Let's see what answer we have here. So vector negative A, because if we're looking at if OA is vector A, BC is moving in the opposite direction, right? So that would be negative A, just to give you that first one to see if you're on the right track and how you're determining it. So you're trying to write everything in terms of vectors A, B, and C. I don't want vertices, I want A, B, and C, everything in terms of A, B, and C.
Did anyone get anything different for A? Just curious.
How much time do we have?
Oh, that's in terms of A.
Yes.
I was gonna.
What is the period in?
4 minutes.
In 4 minutes. Oh, gosh. Okay. Yeah, okay. How about GS, everyone? Anyone have a solution for the next one?
You want to
GS?
get GF?
I hear a lot of A's.
Oh, it's only gonna work on this one. Okay. Vector A. Hooray.
Okay, vector OB. Vector OB. We're representing in terms of A, B, or C. So that's a resultant. Yes? Yeah, don't be scared. Okay, is that correct?
A plus B.
A plus B. Very good. Okay. Vector AC. AC. We have another resultant. We have a negative A plus B. Is that correct, Bennett? Vector B minus A or B plus negative A, right? I think that's very close to what you said. Does anyone want to try? The next one is going to have 3 vectors. I believe the next 2. 3 vectors to get here. BG. I think 3 vectors.
Actually, there's 2 vectors, but 2 different ways to write.
Oh, okay. 2 different ways to write it. Does anyone want to take A? Yes.
Yes. Yes. C minus A is 1.
Okay.
Which is the same as C
C
plus.
minus A or C plus negative A.
Okay, the last one is truly
Oh, F.
3-dimensional,
3-dimensional.
which means we need 3 vectors. So O to F, you're traveling in 3 dimensions across the diagonal.
For all those comp sci students who know how to design in 3D or code in 3D, how this should be easy for you. What 3 vectors? You want to guess? C plus B plus A, is that correct?
I will accept that as the answer,
Yay.
yes.
Good job.
See, it's as easy as ABC.
So remember, kids, we only have a few more minutes. This was just an introduction to the terminology and the concept of vectors. Maybe Mr. Bullock, if we show them a little sample of the 2 questions at the end. We are really going to be focusing on our day 3 classes. So Mr. Bullock will be giving a seminar. I will also be giving a seminar. I think we're in 302 when we're dealing with those aviation, tension, force, vector problems, because we're going to have to incorporate some trigonometry. Resultants cannot always be calculated according to north, south, east, and west so easily. We'll have to incorporate some trigonometry to help us solve real world vector problems. So brush off those MCR skills, and we're going to have to practice our grade 10 and grade 11
Here's what you need. You
trigonometry.
need Pythagorean theorem. You need SOHCAHTOA, grade 10. Remember that? Sine plus tone. You need sine law for grade 11.
law.
You need cosine law for grade 11. More typically are sine law, cosine law for a lot of the problems, because a lot of the triangles you create are non-right angle. Okay. So make sure you're brushing up. We're gonna include a nice summary for what you need to know. Make sure you study those trigonometric laws from grade 10 and 11 because you absolutely need them. for this.
And more specifically, when you come for our consultations, make sure you know when to use the sine law, when to use the cosine law, okay? Will be super important. Okay, we're done for the day, grade 12s, grade 12.
Okay, we will post this to